Hello again. No, this might be the first video that shows up chronologically. Hello for the first time, except that you've been in class already. So, the goal of this document is just to review a little bit more of the stuff that really I regard as prereq stuff for analysis. It's really foundational things. And remember, foundational or prereq doesn't mean easy. It just means foundational or prereq. It's stuff you need to know before you can really do what I want to do in the class. So, let's talk about proving sets are equal, because we'll need to do that an awful lot in this class. So if you have some sets, A and B, if you want to show A is equal to B, well, really you need two things. In fact, this is what equality of sets means. You need to show A is a subset of B, and B is a subset of A. So that means that quite nearly every proof of set equality will have two parts. First, you'll have to show that A is a subset of B, and second, you'll have to show that B is a subset of A. And how do you show that A is a subset of B? Well, what does this mean? That means everything in A has to be in B. So a proof that A is a subset of B will have to begin with some sort of consideration of any element of A. Since it's an element of big A, I'll call it little a, but names don't matter. Consider anything in big A, and it should conclude with the fact that little a is in big B, because that's what set containment means. Everything in big A is also in big B. So if you consider anything in big A and conclude that that particular thing is in big B, then you're done. And this should be the same. This claim should start with a consideration of any little b in big B, and conclude with the conclusion that little b is in big A. And just as a demo of these ideas of proving set equality statements, let's prove some really basic ones. So let's let A and B and C be sets. Here are just some basic set theoretic laws. The union of two sets is that same set. The intersection of a set with itself is that same set. A union B, commutativity, is the same thing as B union A. A intersect B is the same thing as B intersect A. A union B union C is the same thing as associativity means that it doesn't matter where parentheses are. A union B union C. So once we prove this, what this means is if you see a string of a bunch of unions, you don't need parentheses. And same thing with intersections. A intersect B intersect C is the same thing as A intersect B intersect C. And finally, distributivity. A intersect B union C is the same thing as A intersect B union A intersect C. A union B intersect C is the same thing as A union B intersect A union C. And the final basic set theoretic thing that I'll show is De Morgan's law for sets, which is closely related to De Morgan's law for logic. The set difference A minus B union C is the same thing as A set minus B intersect A set minus C. A set minus B intersect C, the union will become an intersect. It'll become A minus B union A minus C. So the idea here is I'm going to go through the proofs of these on some separate sheets of paper. I didn't bother typing anything up. These separate sheets of paper might appear online along with this document. These proofs also appear written up reasonably well in the book, so I don't regard that as a high priority unless you just didn't follow those. So let's do it. So, and in class, like I did a subset of these problems. Here I'm going to do all of them. So, idempotency. Claim. for any set A union A is equal to A, and A intersect A is equal to A. And let's start with the proof that A union A is equal to A. And so this is going to go in a super straightforward way. So let's consider any A in, well, it doesn't matter which one you do first, in A union A. Well then, by the very definition of union, A is in A, or A is in A, right? If A is in the union of two things, that means it has to be in one of the two things. So either A is in A or A is in A. Either way, A is in A. Cool. So we consider anything in the union, and we showed that it's in A. Therefore, A union A is a subset of A. Cool. So let's do the opposite. Let's consider any A in A. We need to show that A is in the union of the two things, so our goal has to be that it's in one of the two things. Well, wait, so this is a statement. A is in A is true. True or true is still true. Then, well, it certainly is the case that A is in A or A is in A. And that's a really silly thing to write, but let's just check that it's true. If A is in A, then are at least one of those two statements true? Yeah, they're both true, but that's allowed in an or statement. Thus, by the very definition of union, A is in A union A, and so A is contained in A union A, since A union A is contained in A, and A is contained in A union A is equal to A union A. Nice. So there's one of the claims done. And I said I would do them all. I think I'm not going to, but I'll at least do both of the idempotency claims. So next thing, let's go through the proof that A intersect A is equal to A. And I feel like I might be including slightly more words than you would want to in the same write-up, and I'm double spacing, but that's because my handwriting's bad. Realistically, you could do this in probably a quarter of the amount of space that I used. Proof that A intersect A is equal to A. So they're going to be the two same steps. So let's consider any A in A. And it doesn't matter which one you do first. Last time I did the union first. This time I'm doing the just A first. Consider any little a in big A. Well, let's check this out. Then, well, we need it to be in the intersection, so we need it to be in both of them. But if A is in A, well, that means that A is in A, and it's also true that A is in A. And again, that's like a super silly thing to say, but if A is in A, then are both of those things true? Yeah, so the and statement is true. So this does indeed follow. Thus, by the very definition of intersection, A is in A A is a subset of A intersect A. Cool. Now, conversely, let's consider any A in the intersection. Then, well, by the definition of intersection, A is in A, and A is in A. But wait, if A is in A and A is in A, right, if you add two things together and get a true statement, that means that both of those have to be true. In particular, if this is true and that is true, then that must be true. Both of those are true. So, just writing down one of those, in particular then, little a is in big A. Hey, wait, but we just started with the assumption that A is in the intersection and showed that A is in A. Cool. Thus, A intersect A is contained in A, and we conclude A intersect A is equal to A as we claimed. All right, cool. So the next one that I said I would address is commutativity. And I am getting tired, and these are all very straightforward. So I think I'm going to accept the fact that I lied. So I'm going to prove one of the results of commutativity. Let's prove, in fact, that A union B is equal to B union A for every set A and B. So let's let A and B be sets. It's important to start every proof with a declaration of what the variables mean. Otherwise, a reader can't tell what you're doing. Even if they're in the theorem statement, you should have declaration of variables. It's important. We want to prove this bit of set equality, so let's let variable name doesn't matter, I'll call it x. Let x be in A union B. Well, since x is in A union B, it follows that x is in A or x is in B. Well, let's think about statements and oring them together. Does it matter what order you take an or in? It doesn't, right? If this is true, then the or is true. If that's true, then the or is true. If they're both true, then the or is true. Thus, x is in B or x is in A, and so x is in B union A. This shows A union B is contained in B union A. And in fact, I think I'm going to lie even harder. I'm only going to do half of this proof. The other half is literally the same. The other half is for you. So let's keep on moving along. Let's do one of the associativity claims. This has a few more moving parts. None of these are, strictly speaking, difficult, but they're worth going through just to demo how set equality proofs go. So let's do the proof of associativity. And in particular, let's just do one of them. Let's prove that A union B union C is equal to, too many parentheses, A union B union C. All right, well, let's do it. So let's let A, B, and C be sets. let's let X be an element of A union B union C. Well, so let's see. That means that X is in A union B, or X is in C. And so maybe this looks like a case-by-case proof, and I'll do it as such. If X is in C, let's take a look at what we want to conclude. There's our goal. We want to get X into there. Well, if X is in C, then it's certainly true that X is in B or X is in C. So X is in B union C. As X is in B union C, it follows that X is in A or X is in B union C. So X is in A union B union C. Good. So that's like exactly the conclusion we want, except we've only done it in one of the cases. There's still a case left to do. On the other foot, or hand as it were, if X is in A union B, then X is in A or X is in B. And it looks like, again, we see two cases. If X is in A, then, well, it's certainly true that X is in A or X is in B union C. So X is in A union B union C, as we desired. If X is in B, then, well, it's like the same logic, right? X is going to be in B union C. And so X is in A union B union C, as we claimed. Thus, right, we boiled it down. We completely exhausted all of the possible cases. For all X in A union B union C, it follows that X is in A union B union C. Therefore, A union B union C is contained in A union B union C. There we go. Of course, again, this is only half of the proof. But again, you can kind of imagine that the other direction of the proof is going to be the exact same. Some of the cases will just be rearranged as all. In fact, what you could even do is you could use the thing that we've already proven together with commutativity to conclude that these things are the same claim. But maybe that's fancier than you need. So let's move on to distributivity. And again, I'm only going to do one of the distributivity claims. Let's do A intersect B union A intersect C is equal to A intersect B union C. And the fact that I copied that down like backwards is probably a clue that I'm getting tired and slightly sloppy. I've recorded a few of these all at once. So I'll go through this proof, and then I think I will take a break. Not that you need to know that, right? They'll be uploaded appropriately. You don't need to know that I'm recording many at the same time. So let's prove that. So you want to prove something about set equality? So let's let x be in, well, it doesn't matter which way we do first. Let's do the forward direction first. A union, intersect B, union, well, no, you should start with declaring variables. Let A, B, and C be sets. And then we'll let x be in A intersect B, union A intersect C. So what does that mean? Well, I see a union. So x is in A intersect B, or x is in A intersect C. So let's just deal with both of those. If x is in A intersect B, let's just take a look at what happens. Then it must be that x is in A and x is in B. So let's take a look at what we need. We need to conclude x is in A intersect B union C. So we need x is in A. We already have that. Great. X is in B. We need it to be in B union C, but that's like an OR, so we can deal with that. Since x is in B, it follows that x is in B or x is in C, so x is in B union C. Since x is in A, as we already concluded, and x is in B, a union C, that means that x is in A intersect B union C. These parentheses do matter. Which is exactly what you needed to conclude, except that you've only dealt with one case right now. If x is in A intersect C, then, well, maybe I'll do something that's a slight cop-out. The same argument as above gives x is in A intersect B, a union C. And I encourage you to convince yourself that it's the same argument. Thus, either way, for all x in A intersect B, union A intersect C, it follows that x is in A intersect B, union C. And so, A intersect B, union A intersect C is contained in A intersect B, union C, which is exactly what we needed. And so there's one more claim to do here, and I think it is sufficiently different that I will in fact do it. So we'll see how I do for space. X be in A intersect B union C and see what we get. And we better get that, right? We better get x is in this. All right, well, let's do it. I see an intersection. So x is in A and x is in B union C. And let's take a look at what we want to conclude. There's what we want to conclude. We want to conclude x is in A intersect B union A intersect C. So we want to conclude x is in A intersect B or x is in A intersect C, we already have x's in A. So let's expand this piece out. Since x is in B union C, it follows that x is in B, or x is in C. And that's, I mean, there's an or statement, so there's like a case-by-case thing we could do. If x is in B, then, let's see, we have x is in A and x is in B. Then we get that x is in A and x is in B. So x is in A intersect B. Since x is in A intersect B, it follows that x is in A intersect B union A intersect C. Because right, if x is in A intersect B, then it's certainly in A intersect B, or it's in A intersect C. So you get this conclusion, which is exactly what you want. But that's not all the proof, right? There are cases. If x is in C, because of this or statement, then what do we have? We have x is in A, because we assumed we have x is in A like the first step. And x is in C, so x is in A intersect C. Since x is in A intersect C, it certainly follows that x is in A intersect C union with some other stuff. So what do we see? We see either way, we get x in A intersect B union A intersect C, parentheses matter. So A intersect B union C is contained in A intersect B union A intersect C. And so, since we proved that this containment happens and that containment happens, what can we conclude? We can conclude A intersect B union A intersect C is equal to A intersect B union C, which is exactly what the theorem claims. Great. And the last one on the list to do is De Morgan's law. So what does De Morgan's law? Says that for all sets A, B, C, A set minus B union C is the same thing as A set minus B intersect A set minus C. It also says another thing, but just like the past couple, I'm only going to prove one of the results. Just in the interest of my own voice, it is getting tired. So let's try to prove that. So let's let A, B, and C be sets. Let's let x be an element of A set minus B union C, so that x is in A and not x is in B union C. So let's expand that out. We have x is in A, so we'll just hold on to that. And let's just expand this next bit out. So since the negation of x is in B union C, it follows that, well, let's keep the negation in there for a little bit longer. It follows that not x is in B, or x is in C. So now think about this. What does not do to an or? It turns it into an and both of those statements will get negated. Thus, x is not an element of B, and x is not an element of C. So let's just put everything together. Let's look at the goal. We need x to be in A set minus B. So we need x is in A and not x is in B. Do we have those? Yeah, we have x is in A, we have x is not in B. So since x is in A and x is not in B, it follows that x is in A minus B. Good. And presumably that'll be like the same. We need x is in A. Sorry, I think there's been lots of pointing off of the paper today. X is in A and x is not in C. We need that to get this conclusion. Do we have them both? Yeah. X is in A, x is not in C. Since x is in A and x is not in C, it follows that x is in A minus C. Since x is in A minus B and x is in A minus C, it follows that x is in A minus B intersect A minus C, which is exactly what we needed, right? So, one last thing, I guess we have to do the opposite direction. Conversely, let's let x be in A minus B intersect A minus C. And let's try to prove that x is in A minus B union C. Or rather, yeah, x is in A set minus B union C. So let's try to do that. So since x is in this, there's an intersection symbol. So x is in A minus B, and x is in A minus C. So let's just put this all together. So x is in A, and x is in B, since x is not in B, rather, since x is in A set minus B. Similarly, x is in A and x is not in C. So let's look at those two in particular. So notice x is in B, not in B, and x is not in C implies, so I'm going to do like some logical calculus here. Not x is in B, and no, actually, I don't want that parenthesis. And not x is in C. So I'm negating two statements. There's an and between them. So I know what that does logically. I can pull the not out and turn that and into an or. So not x is in B or x is in C. But look in there, x in B or x in C, that means x is in the union. Thus, x, or rather not, x is in B union C. So now let's just gather things together. So let's see, since x is in A and x is not in B union C, it follows then, well, x is in A and x is not in this other set. That's exactly what set difference means. As we claimed. And that proves De Morgan's law, or at least proves half of De Morgan's law. The other one is left for you to do. All right, cool. So that concludes this little lecture. It went on longer than anticipated, almost 40 minutes. But hopefully you'll find it useful. All that has happened is so we've gone through some examples. Great. So I'm going to continue to not know how to close these little mini lectures and just say bye.